Hi there, this is a short video to talk a bit about how to find eigenvalues and eigenvectors for square matrices. So what's an eigenvalue anyway? Let's say you've got some square matrix A. If a vector and a scalar exist such that A times the vector is equal to a scalar times the vector, so x is some vector, lambda is equal to some scalar. If the vector and the scalar exist such that your matrix times the vector is equal to some scalar times that vector, then the scalar is an eigenvalue of the matrix A. And x, the vector, is an eigenvector of the matrix A. And these eigenvalues and eigenvectors come in pairs for obvious reasons. Right? This eigenvector corresponds to this eigenvalue, and they produce the same effect as multiplying A by x. So why do you care? You can probably see how being able to multiply a vector by a scalar instead of your matrix might be handy for a lot of matrix population models. For example, if I have some matrix, like a square Leslie matrix, that I'm using to project my population forward in time, if I can find an eigenvalue for that matrix, I can replace a lot of tedious matrix multiplication in exponential models. Remember that models that look like this, where here A would be your projection matrix, usually a Leslie matrix. So if we can find an eigenvalue for that projection matrix, instead of multiplying this matrix times itself t times to find the population at size t at time t, we can just multiply the initial population by this scalar. You will note this is why we often use lambda for population growth rates. It's the same one we use for eigenvalues. Not a coincidence. Anyway, how do we find eigenvalues for our matrix? Well, we're defining this to be true, that our matrix times the vector we want is equal to some scalar constant times the vector we want. First, we're going to assume that our eigenvector x is not a zero vector, which means we can rearrange this to say a times x minus lambda times x is going to be equal to 0. It's tempting to try and factor out the x right away, but remember, A is a matrix, a square matrix, and lambda is just a scalar, it's a number. And you can't subtract a single number from a matrix. So first, we're going to multiply lambda x by the identity matrix that's the same size as A, or has the same number of rows and columns as A. So now we get a times x minus lambda times I times x is equal to 0. If you remember, the identity matrix is just 1 on the diagonals and 0 everywhere else. I think I've got enough zeros in there, yeah. So multiplying lambda times the identity matrix doesn't change the value of this expression, it just turns lambda into a matrix where instead of ones you've got lambdas everywhere. Give it a try if you don't believe me. So now that we've got a matrix minus another matrix, we can factor out the x, which means we get A minus lambda times the identity matrix times x is equal to 0. Since we already decided that x is not equal to 0, that implies that the determinant of this other matrix, A minus lambda I, is equal to 0. This might seem like a bit of a jump from, because we know x is not equal to 0, the determinant of this must be 0. But there is a rule of matrices. If A times some vector is equal to 0, and x is not equal to 0, A is what you call singular. Singular matrices have couple of interesting properties. One is they don't have an inverse, and two, their determinant is always 0. So to go back over here, since this matrix times x is equal to 0, that means the determinant of this matrix must be 0. So what good does that do me? So we've decided that the determinant of a minus lambda I is going to be equal to 0. I'm going to do this for the case of a 2 by 2 matrix because it's easy to see and small, but this is going to apply to any square matrix. So let's say A is a 2 by 2 matrix, so it's got A11, A12, A21, and A22 are its elements. So that means A minus lambda times I is going to be equal to A11 minus lambda times A12, A21, A22 minus lambda. Remember that the determinant of a 2 by 2 matrix is A times D minus B times C. So the determinant of A minus lambda I is going to be A times D, A11 minus lambda times A22 minus lambda minus A12 times A21, which gives us a quadratic that looks ugly because it's full of variables, but is actually very rarely that complicated. And if you want to be picky about it, you can simplify it to this, because A11, A22 minus A12, A21 is just the determinant of the original matrix, A, is equal to 0, right? Because we said that this determinant was going to be equal to 0. So now we have a fairly straightforward quadratic that we can solve to find our values of lambda that are our eigenvalues. And in general, there will be as many values of lambda as your matrix has rows. So I'll just do an example, because it can get confusing with all those A sub whatevers. So let's say my matrix is 1, minus 2, 1, 4. Well, then my A minus lambda I is just going to be 1 minus lambda minus 2, 1, and 4 minus lambda. The determinant of that is going to be 1 minus lambda times 4 minus lambda minus 2 times 1 is equal to 0. So the quadratic we get, which is called the characteristic equation of your matrix, incidentally, we end up with lambda squared 5 times lambda plus 6 is equal to 0. And we can factor that and get lambda minus 2, lambda minus 3 is equal to 0. So lambda is equal to 2 or 3. So, voila, those are my two eigenvalues of the matrix A. Now that I have my eigenvalues, how do I find my eigenvectors that go with them? Well, we decided, remembering from the last page, for the matrix 1, negative 2, 1, 4, the eigenvalues we got were 2 and 3. Since at the very beginning, we decided that A minus lambda I times our eigenvector is equal to 0, we can just sub in our eigenvalues to get back what their corresponding eigenvector is. So A minus lambda I, when lambda is equal to 2, gives us 1 minus 2, 1, and 4 minus 2. So that gives us minus 1, minus 2, 1, and 2. And since we defined earlier that this matrix times our eigenvector x is going to equal 0, we can say that x1 times negative 1 plus x2 times negative 2 is equal to 0, and x1 plus 2x2 is equal to 0. So these are the same, just multiplied by negative 1. So in the end we get x1 is equal to negative 2x2. So this requirement will be satisfied by all vectors x that are any multiple of 1 minus 1/2, where k is just some scalar multiple. Which reminds me, that's another important thing to remember about eigenvectors, is that they're still eigenvectors if you multiply all the elements in them by the same scalar multiple. It's actually the relationships between the elements that matter. So quite often you'll see eigenvectors written in this form as some constant times a simple form of the eigenvector. Right? But wait, we've got to find the other eigenvector, because this one is the eigenvector that goes along with lambda equals 2. What if lambda is for the other eigenvector, for the other eigenvalue, sorry, we get a minus lambda I being 1 minus 3, minus 2, 1, 4 minus 3, which is minus 2, minus 2, 1, minus 1, which gives us minus 2x1 minus 2x2 is equal to 0, and x1 minus x1, sorry, that's positive, x1 plus x2 is equal to 0, which means x1 is equal to negative x2. So if lambda is equal to 3, x can be any vector of the form 1, negative 1. Just review the steps for finding eigenvectors and eigenvalues. 1. Remember that a times x is equal to lambda x implies that a minus lambda times I x is equal to 0. And you want to find the determinant of a minus lambda I. Set it to 0. Solve the characteristic polynomial. For lambda. And then plug your lambda back in to the matrix A minus lambda times I to get the eigenvectors. Or, if A is some matrix, you can just ask MATLAB what the eigenvalues of A are, and it will tell you. When you're out finding eigenvalues and eigenvectors on your own, there's a couple of tricks to check your work. For any matrix A, the product, this is a big capital Pi, that means the product of all the eigenvalues is equal to the determinant of your original matrix. So once you have your eigenvalues, if you multiply them all together, you should get the same result as if you take the determinant of your original matrix A. Also, the sum of your eigenvalues should be equal to all of the sum of all the diagonal elements of A. Right, so if A is some matrix, the diagonal elements are the ones that have row 1, column 1, row 2, column 2. The sum of all of those should be equal to the sum of the eigenvalues. Handy tricks for checking your homework and making sure you're not making simple arithmetic mistakes like I do all the time. And that's really all I wanted to say about eigenvectors and eigenvalues for now. So thanks for listening.